It will be basically a literature review section, and the literature review section will have an accompanying report to it. The topics that will be covered are, and I will go over them, I will give you an info session and then I will go over the different topics, are related to recent research on in-memory computing or on approximate computing. And so basically the first topic is non-volatile adder design, and I will explain this in a bit. Approximate adder design, non-volatile memory technologies, and SRAM-based neural network accelerators and RRAM-based physical unclonable functions. I will explain to you about each one of this topic what it is. We do not expect that you will be basically understanding the details of implementation as much as the objective is to identify recent research papers and understand the advantages and where the state of the art is. Yani, we would like you to look through recent IEEE transaction papers, which are journals, Nature journals, and other high impact factor journals as your references. And let us focus on the IEEE, mainly the IEEE transaction papers. Hello. The way the report will be organized or graded will depend highly on the quality of the work. And be sure to provide all the relevant information and be sure to be organized, concise, and complete. The conclusions are complete. يعني مثلا لنقول إذا لقيتوا 2 or 3 papers about a certain topic, let us say, for example, ARM-based adders or adders using non-volatile memory. At least put a conclusion table towards the end that compares or places the claims, for example, of the authors. Let us say, for example, citation number 1, if they have the area, if they have any information about the power or energy, if they have information about the latency, then make sure you put, for example, even if you cannot, if it is not fair because it is not apples to apples, and here you would put, for example, note the contribution. Okay, for example, this claim that they have developed a 3-transistor-based full adder, for example, or a new XOR gate to implement the adder. Okay, so put what sounds, although it is not well known in terms of technology to you, and I will explain things in this lecture, but at least try to capture the claim. Assume you're in a consulting company, you're telling your boss, well, what's happening out there on this topic, and you want to capture the claims that the authors have stated, okay? In addition to this, it is good to try, for example, to go back to the basics that you know. For example, we know that an adder is a XOR function, relies on XOR, or a tutorial that would tell us the basics, and oh, okay, so this they are defining. We know how to build the XOR in CMOS, but it is costly. It takes, for example, 8 transistors. Those guys are using the memristor and 3 transistors, and I will talk about this information next, the technical information next. Hello. We would like, when you submit the report, to have ECE for 12_family name.pdf, family name of the first group member sorted in alphabetical order. يعني مثلا family name, for example, let us say we have family name Ahmed and family name let us say Tabish, and family name I don't know, something Zara'at, let us say. Okay, so the family name Ahmed will be submitting the report in the name of the student whose family name comes first alphabetical order. Okay. The quality of the report is an important major part of the grade. So let us look at what is required for the quality of the report. Basically, it should be clear and concise, and very well organized, straight to the point. You have titles, you have subtitles. Okay, for example, let us say you read 4 papers. The first paper is about novel XOR gate-based adder. Okay, so your main intro, you will have an intro section basically. Then you will talk what will you cover towards the end of the introduction in this report, and then section number 1 or chapter or let us say section number 2 will be for this XOR based adders. You will refer to the paper where you got this. There will be another section 2.1 that is talking about, for example, the XOR gate, and then 2.2 the adder implementation. Okay, and then section number 3 will talk about something else, the other papers, 3.1, 3.2, and then section number 5 will be, for example, comparative analysis or a discussion, and in the discussion you will build a table where you compare what you have read. Okay, and then the conclusions section will come after that. Okay, so make sure that you are systematic in your write-up. You're passing the message, you're clearly showing what you read, that you went into each paper and extracted the info that you could extract, and then you did comparative analysis, and then you wrote your conclusions. Of course, there has to be basically an introduction that defines the topic and its importance, and you will find this in all the introductions of all the papers. The minimum number of papers to be reviewed is around 4 papers. Of course, if somebody reviews more, then the grade will be higher, but this is the minimum requirement. Then the report length, and you will get basically a plus compared to your colleagues. The report length should be minimum 6 pages, excluding the front page. So the clarity and the conciseness and the presentation of the report, you have to have a front page where you say the group name, the topic, okay, and then a table of contents, the references, and the conclusions, contributions. Okay, so there is going to be a reference page where you state the references that you read, that you are referring to through the whole paper, and there is going to be a contributions page. So the core, meaning the intro, hide a report length. This is covering basically the intro, the sections, the technical sections, okay, and then the conclusion parts, okay, and then there has to be also, in addition, a front page, a table of content, the references, and the contributions. Okay. هلا طبعا ما تحطوا لي 6 figures on 6 pages and the report is done. يعني there has to be material, some material into it. هلا also there's a grade on it being state of the art. يعني مش مثلا you found online the first Google reference you found from 1967 and you put it here. It has to be recent papers. Okay, and recent papers, typically the last 3-4 years, is great. Explanation of the technique, and each paper that you read, you try to extract the parts where they are saying what their solution is, maybe trying to understand the high-level contribution. And then there has to be also illustrations, some figures for every paper. There is the design, and then the conclusions. Future work, if the authors have stated the future work, please make sure you include it as well, or there has to be also the comparative analysis or the discussion where you see from your readings where people are heading next. And then there is the references, okay, and then there is a contribution section. The references have to be like IEEE. The first mentioned reference, text number 1 in your text, and so on and so forth. And the contribution section stating the responsibilities of each team member, and each member what they read, what they did, and stuff like that. هلا there will be turned in for the project. يعني copy paste will not be accepted. Grades will be deducted from the report. So please make sure that you do not copy paste things. Please paraphrase. This is more like an exercise for technical writing, for critical thinking. So let us make sure that this works, and it will be compared against this year and previous year reports. هلا please do not cheat. يعني ما حدا ينقل report من رفقاته يكون copy paste عنهم. A zero tolerance policy would be enforced regarding cheating. Put your effort. The guidelines are clean and clear. If you follow these guidelines, we are not expecting you to come up with maybe innovations. We are expecting you to read the state-of-the-art literature, try to extract the info from it that is reasonably clear to you, and then express it in a clean and concise and clear report following the guidelines. So if you put good effort, you will get a decent grade. Okay, this is as far as the technicalities of the report of the project. Anybody has any questions? هلا طبعا بال 6-12 grading is different. It is a more involved part, so I'm synchronizing with the students on that, but these are the general guidelines for the report. Now let me go over first the memristor technology. Let me first cover for you the memristor technologies. Okay, and then we will talk about memory design, and then we'll talk a little bit about adders and about approximate addition. طيب هلا typically we know that we have three elements in circuits, which are the resistor, the capacitor, and the inductor. Long time ago, scientists said, well, we know that we have three quantities, the voltage, the current, then the flux, and the charge. And they felt, well, we know three elements that relate these quantities to each other. For example, V is equal to Ri, and then dphi equal to LDI, and then the capacitor relates CQ to CV. So there has to be an element that relates the flux to the charge. And it took the scientists maybe 30 some years or more, 40 some years to discover what they call the missing element. So in HP Labs in 2008, they were able to realize this memristor element. The nice thing about this memristor element is that it really benefits from the scaling of technology. يعني نحن لما حكينا عن الترانزستور العادي نحن عندنا كان NMOS أو PMOS كان بالشانل الإلكترون عم يمشي من اللو فولتج الإلكترون يعني الكارنت عم بيروح من الهاي لللو والإلكترون كان عم بيروح من اللو attracted to the high. اوكي هيدول البارتيكلز كانوا عم يمشوا هن عم يخلقوا لنا كارنت. بالممرستر اللي صار انه صار عندنا little particles or the little ions or the material of the transistor صرنا نقدر نعمل عليها كنترول مثل ما الالكترون بيمشي due to applying a voltage difference. اوكي لقوا انه الايونز or the particles themselves can also move when we apply a voltage difference, but this was realized under two conditions. أول شيء إنه أنا the scale of my device is very small، يعني هي بالنانومتر لا أقدر أعمل عليها control وأجذب أو ألقط هالions. And the second thing, the voltage that I apply is higher than the typical voltage يعني منه 1 volt مثل current technology, it is 2, 3 or even 5 volts اللي هي عادة تستعمل للbigger devices. So V is high. Okay. هلا what happens is that they found, although if we have an insulator, okay, if we have an insulator material اللي هي مش مفروض تمرق لنا current, okay, if somehow they stress it or apply, هيدي طبعا هيدا الالكترود اللي لها and it has a bottom electrode, if they somehow stress it or apply some high voltage or they call burn in, okay, حيخلقوا some form of a filament, okay, وهيدا الفيلامنت هو بيقدر يخلق لي a resistive path, or if they de-stress it or apply the opposite voltage, then they will somehow program the filament to eliminate the resistive path. يعني اللي عم بيصير هن في عندهم ions, يا أما الفيلامنت is empty and this creates a low resistive path, بصير في عندي connection بين هالpoint, هيدا هو بصير low resistor, يا أما I practically push these ions away to create a gap, ببطل في عندي connected path, بصير في عندي a high resistive path, بصير الكارنت اللي عم يمرق هون small أو تقريبا إذا بدنا نعتبره infinity يعني it is an open source. فإذا أنا I can now manipulate the material such that the material acts like non-volatile memory. شو يعني non-volatile memory؟ هات لنشوف. Let us first talk about two things, and let me exactly, this means that it retains its state point. So let me stop sharing and I will let me stop sharing and I will share a little bit the screen from here. So typically what we have is the following. In regular memory design عادة نحن we have what we call volatile memory. Okay? وهال volatile memory it tries to store the bit information. يعني نحن حكينا أنه نحن الانفرتر عنا إياه it stores if I put a 0 here I will get a 1. Now if I connect two inverters back to back, the one that is applied here will drive the 0. طيب هذه هي البيسس to what we call SRAM cell. Okay, so the SRAM هي random access memory, and it is basically what it does is that it can store a bit value. Let us look how the SRAM cell holds the bit value. The top inverter, okay, is a PMOS and an NMOS, okay, and it is connected to VDD and ground. The same for the bottom inverter. The bottom inverter كمان عنده PMOS و NMOS. It's a simple CMOS inverter, and it is connected to VDD and the ground. The output of the first is the input to the second, and the output of the second is the input to the first. Let us say, without loss of generality, that I stored a 0 here. The 0 is going to turn on the PMOS, turn off the NMOS. It is going, the PMOS will pull up this node to 1, to VDD basically, okay? And then the VDD will arrive at this node, the NMOS will be on, the PMOS will be off, and the NMOS will pull down this node to 0. So this back-to-back inverter will basically store if we are reading the left node, it will be storing a 0 bit. And as long as VDD is on, okay, then as long as the chip is powered, I will be able to hold this 0 and 1 bit. Now, let me assume that I am reading, typically when we read from both sides and look at the voltage difference. Let me assume that I am reading only the right-hand side. So this is really, I can say this is storing a 1. Now, what if the power goes off? The chip is powered off. What happens? If the chip is powered off, VDD basically will drop to what? هتروح ال VDD على 0 صح؟ هتروح ال VDD على وين؟ على 0 صح. So we will lose the data. But why we lose the data? Here we have 0 and 0. خلاص أول شيء يعني we're going to discharge basically. وحتى لو اعتبرنا إنه ال PMOS is on, okay, then this will become إذا هيدي صارت 0 فعليا وهيدي 0 قلب صار العالي هو السورس. Okay, and then this will drive and this will discharge لأنه هيدا هو it is now a capacitor that is charged. Okay, and the supplies to the chip are all zeros. Okay, if the supplies are all zeros, any node in the chip will be between, the supply voltage will be between what? V supply and the ground. بس ال V supply لإلي صار زيرو، يعني خلص كل النودز رح يعملوا discharge للزيرو. So هاي رح تروح رح تطفي ورح بتصير زيرو. Okay, so this will turn off and it will become 0. Exactly. So the output is dependent on the power that we are supplying. يعني there will be a resistive path that will connect this capacitor that was pre-charged to ground, and it will turn off and everything will discharge and turn off. Okay, طبعا إذا هاي 0 هيدا كمان off وخلص طفى كل شيء. فthis is why we call it volatile memory. ليش؟ لأن ال volatile memory it is going to lose its stored values. Okay, so the volatile memory is going to lose its stored values. هلا, what is the SRAM really? The SRAM cell is designed like this. لأنه في عنا نحن SRAM based neural network accelerators. The SRAM cell is designed like this. عندي ال back-to-back inverter. عندي هون transistor وهون transistor that really acts as a switch. Anytime I want to write to the cell in a simple fashion, I will apply one here and one here to turn on those two transistors لأنه NMOS is active high, and then I apply a 1 and a 0. If I want to write 1 on this side, then I will be helping the inverters to drive this node to 0 and to drive this node to 1. Once the values latch in, then those transistors will turn off, and then the cell will basically store the 1 and the 0 on both sides. Okay, so هي بترجع بتعمل sustaining لما هو transistors يطفوا بتعمل sustaining للvalue اللي انكتب عليها. طبعا there are many issues with variability and other stuff, but this is for a typical design. هلا, when we want to read the cell, what we do is we pre-charge this capacitor to high. So بنحط عليه V init equals to high, and here we put pre-charge this capacitor V init equals to high. Okay, so ببلشوا هيدول النودز عاليين هون. هيدي النود ببلش عالي, and then after that this is step number 1. Step number 2, we turn on these turn on what we call them the pass gates. So هيدا حيدور وهيدا حيدور. step number 1 هي بتكون pre-charge. we call them the bit lines لأنه عم نبعت البت info عليهم. هيدول عادة بنحطهم opposite لبعضهم وقت الرايت بيكونوا مثل بعضهم وقت الريد. and then step number 3 what's going to happen. هون عندي 1 وهيدا هاي ما حيأثروا على بعضهم. هون عندي 0 هيدا هاي فحينجر هيدا حينجر الكاباسيتور through to this 0. so بنشوف هيدا نزل شوي بينما هيدا بدله عالي. the voltage difference VBL minus VBLB هو اللي بيحدد لي أنا على أي جهة عندي 1 أو 0. أوكي لأنه إذا VBL أكبر من VBLB basically حنحطهم نبعتهم على sense amplifier أو comparator. هيدا بيعني عندي 1. إذا بالقلب هيدا بيعني أنا I am storing a 0 لأنه نحن we are always consistent. we either read the left side or we read the right hand side for the data stored. Okay. So Paul, you have a question. If both input outputs are 0, what's the output on turn on? لما نرجع نعمل لها powering on, it will have a random value. So then we have to write into it data. لأنه because of variability, it can initialize حسب أي side slightly stronger than the other. It might have a random status. Okay. Hello. Why is pre-charge and find the difference instead of just reading from one output? There is another version of the SRAM cell يلي هي اسمها 8T SRAM cell. And this 8T SRAM cell is single-sided read. Okay, so هيدي اعتمدوا فيها single-sided read. And the way it looks like is as follows. So نحن عنا هيدي السيل. Okay, وهيدول الباس gate transistor. This port is used for writing. وحتى ما يصير noise على السيل وقت الريد. What they did is they added 2 more transistors. عادة هن بيحبوا الcompactness. يعني قد ما كانت صغير الأسرم سيل قد ما بتكون الميموري more compact. Okay, and so what happens is that ليخلصوا من النويز that is injected to the cell اجوا قالوا طيب أنا هحط 2 stacked transistors هون. Okay, and this will be connected to something I call the read bit line. The read bit line is initially pre-charged. So هيدا VNE عليه equal to VDD. And when they send a read pulse, هيدا read word line يعني عليه read pulse. Okay, if the cell is storing a 1 on this side, then this will turn on and those will discharge the read bit line. Okay, so ساعتها بنعرف بس بالقلب اللوجيك هون طبعا بدهم يعدلوا لوجيك بنعرف انه انا I am storing a 1. The issue with this is that this requires 8 transistors يعني my memory is bigger now, but the pros of this is that now I'm not injecting noise during read onto the cell. Okay, so yes, there are different versions of the SRAM cells. Okay, so هيدي هي it's a volatile memory كمان نفس الشيء it will suffer from the same. هلا other types of volatile memory هن dynamic random access memory. So هيدي هي static random access memory الأسرام لأن بس نكتب الفاليو ما بدنا نعمل له refresh. الدايناميك random access memory هي عبارة عن one transistor معه capacitor كبير. Okay, and basically it is not like this, pardon. And basically this single transistor is used to write يعني to charge or discharge the capacitor. المشكل هون عنده bit line وبنكتب هالكاباسيتر، يا الكاباسيتر stores VDD أو it stores 0. And when I'm reading, I try to see if I'm storing a 0 or a 1. The problem with this is that it needs refresh، لأنه نحن في عنا leakages ممكن هيدا يعمل leaking. بالأسرم ما في عندي leakages حيصير لأنه هيدا ماسك هيدي النود وهيدا ماسك هيدي النود. So the feedback maintains the state of the SRAM cell. This is as far as the volatile memory is concerned. So let us see now لما اجوا عملوا هيدول new devices وطلعوا ب different types of non-volatile memory. you are familiar with other types of non-volatile memory يلي هن مثل الفلاش memory وال USB and all of this stuff. بس هيدول they used to consume area and their speed was very slow. هن كانوا عم بفتشوا عن volatile memory that can be integrated on the chip, non-volatile memory that can be integrated on the chip and whose area is really small. So with this new memristor, they were able to say, well, now if I apply on this device a high positive voltage, then it is going to become مثلا R low, and all of a sudden I will have this R low with an access transistor, okay? And now if I have a capacitor and I turn this transistor on, if this is R low, then this capacitor will be discharged. But if I have programmed this device to be R high and I'm trying to discharge a capacitor, whenever I power on and turn on this transistor, this is going to be slow discharge. And basically the output will be slow versus here, the output will be very fast. And we will know from this delta V whether I am storing a 1 or a 0. Okay, so هيدي حتى لو طفت الباور على الشيب, so long I have programmed this memristor to this value, I don't have any issue. I can power it off, go away, then power it on, and my state will remain saved in the memristor value. So this is very important. Let us see what are the features, why memristors are important. What are the features that made them now be integrated on the chip? Okay, and then we will talk a little bit about how they are used in logic or how they are used in other types of PUF design or variability-based security hardware blocks. Okay, so let me stop sharing from here and let me share again from the main screen. Okay, so as far as this memristor therefore is concerned, what we found here is that we can program it. What's a memristor? They said, well, anything that is a two-terminal non-volatile memory device, then it is a memristor. Okay. في different types of memristor. Some of them that rely on magnetic properties, and some of them rely on the dielectric or the oxide properties. يعني الفيزيكال ستراكشر كيف انعمل اختلف. مع اختلاف الفيزيكال ستراكشر بيختلف معنا الرينج بين الار لو للار هاي. مثلا هيدي لنقول من 1K ل 10K، بينما الرينج بهاي في يكون مثلا من 50K ل 1 meg. And this matters. We want a good ratio of R high over R low. لأنه كل ما كبر الريشيو كل ما كبر الفرق بالكرنت وقدرنا to manipulate the analysis better. And then there is also the property of, well, how robust is my design. يعني this magnetic based design خلص ال R low بتطلع R low على قد وال R high بتطلع R high على قد. بينما هون عم بيكون عندنا distribution فيهم، يعني ممكن ال 50 توصل لل 150 مثلا، وال 1 meg ينزل ل 300. So we need to design for these variations and take them into consideration. So كل device إلها pros and cons. هلا الRRAM device specifically عندها interesting properties اللي خلتها تكون amicable or favorable for chip design. نحن لحد هلا مثلا the flash is not integrated on the chip, it's on the USB for example, or dynamic RAM عادة بيكون عندنا CPU، بيكون عندنا L1 cache اللي هي أسرع very compact, then we have L2, L3, and maybe they will put the DRAM in the third level cache لأن it is designed, its capacitor takes area and it needs refresh and stuff like that. So في distance بين البروسيسور، هالشيء بيعني لنا إنه في عندنا lag. كل ما كانت أقرب للبروسيسور الميموري كل ما أسرع قدرنا نوصلها، وهلا حنحكي شو معناته الميموري كومبيوتينج بعد شوي. طب اجوا طلعوا على هيدول قالوا إنه أوكي أنا بدي أشوف هي قديش كومباكت. يعني الRRAM بتاخد 1 نانومتر كيوب مثلا. الانرجي تو رايت طبعا هيدول حسبوا لهم الريفرش and other stuff. And then the time to write مثلا الفلاش is very slow. اوكي، وعندنا له مترك اسمه space action metric، يعني اللي هو جولز ضرب نانو سكند ضرب نانومتر كيوب، ليشوفوا هي قد ايه بتصرف انرجي وقد ايه بتاخد وقت وقد ايه بتصرف لفوليوم، تاخذ لي فوليوم على الشيب ككومباكتنس. ولقوا انه الRRAM عنده smallest space action metric. اوكي، so it is basically very favorable. ورجعوا قالوا انه هي بدها يساعدها لندورها لحتى نعمل مثلا لما قسنا الكرنت اللي قاطع هون بدي احط لها سويتش، وهالسويتش عاده بيقدر يكون ترانزستور يلي انا بدوره لشوف قديش كرنت عم يقطع، او بطفيه اذا انا ماني معاوزه to evaluate لشوف قديش I am storing here. So this is the benefits of the RRAM. It is compact, therefore we can integrate it with transistors and we can integrate it on the chip. مش بهمنا الانرجي efficient design، بهمنا الانرجي efficient design لانه نحن هلا البيج داتا عم تتطلب كثير analysis or computations. اوكي، ونحن اذا بنقارن الهيومن برين بال really how much the chips are consuming in terms of energy، بنلاقي انه نحن في عنا كثير computations اذا بنعملها approximately maybe we can design what we call a neuromorphic computing، يعني we can try to mimic the model of the human brain. وهلا بنحكي كيف بعد شوي. طيب for the big data مثل ال IoT والautomotive و other stuff في عنا neuromorphic computing اللي هو بيعتمد كيف البرين النيرف يا بيوصل يا ما بيوصل السيجنال. نفس الشيء الميموريستر إذا كان R high أو R low حيوصل أو ما حيوصل السيجنال، يعني أنا I can program it to be R high or R low. طيب وكمان in addition to neuromorphic computing الميموريستر نقدر نشتغل فيه بالنون فولاتايل بروسيسورز. هون non volatile processors مهمين لنا بالسنسورز اللي بنوزعهم، لأنه we are throwing many sensors for agriculture, on the road, etc. and we power them say from the sun or they have limited battery time somewhere, and therefore we need to turn it on and turn it off as needed. And the RRAM or the volatile memory is compact, it can be implanted on chip and it can store my data. وكمان فينا نستعملهم بالin-memory computing والhardware accelerators, and this is why we can overcome and this helps us overcome what we call the memory wall يعني رح نحكي عنه شوي تاني. So فإذا we see very promising applications for this. فلا خلينا نحكي شوي what is the memory wall، بس خليني أمرقكم على هول سلايدات شوي. Okay, so and here we are talking about a neuromorphic computing and what we are saying. خلينا أعملها slide show بس 1 second. Okay, so neuromorphic computing لكان بيعتمد مثل ما قلنا انه النيرف عنده synapse. if I apply a voltage بصير في connection, if I apply an opposite voltage or the depreciating voltage بتفل connection. نفس الشيء الممرستر is programmable. اذا حطيت له positive pulse بصير R low, اذا حطيت له a negative pulse بصير R high. So we'll talk about that later. So the memristor-based neuromorphic computing accelerators بحسنوا الانرجي بالheterogeneous computing, and this is all aiming to mimic the low power operation of the human brain. Okay? يعني نحن بنعمل كذا operation with few watts. Okay? هلا كمان volatile memory عادة نحن مثل ما قلنا في عندي registers بقلب السي بي يو، في عندي كاش اللي هي اسرام، في عندي main memory اللي هي دي رام، وبرجع عندنا secondary storage اللي هي الهارد درايف. And we really move, when we are doing a program, we really move or carry the data from one place to another, and mainly most of the computations بتصير directly بين الأسرام والكاش. So non-volatile memory we can integrate with the SRAM, the memristors, so that we can back up the data into the memristors, or we can perform directly in memory compute using the novel memristor-based associative processors or vector-like processor. بس هيدي بتساعدنا basically بالستاندباي. هلا قصة memory computing شو memory wall? What is the memory wall? Typically, we have the memory مثل ما قلنا عنا L1 cache, L2 cache, and stuff like that. Every time we want to do computation, we go and fetch the data, we store it in the register, then we perform the computation with the ALU, and then we send back the data and we store it in the memory. طيب بس أنا I have lots of multiply and add. يعني بالneural network I have lots of multiply and add, for example. So this is the von Neumann architecture, but there is a bottleneck. لأنه إذا الداتا كبرت كتير بدي أعمل كتير fetches, eventually the performance of my processor will be choked by the transportation time on the bus. Okay, and the ARM-based in-memory compute basically tries to localize the computation. يعني ليش ما نحن فينا نعمل small modules that perform the multiply and accumulate that are embedded together with the stored data, وهلأ رح نحكي كيف in a second, and such that now I can read, perform the calculation, place the result, and then send this result to another module that performs the same. يعني the basic idea إنه خليني أعمل localized processing units that also store the memory مثل بالbrain. Okay, and in addition to this, those hardware accelerators, let them be dedicated or specific to the application at hand. يعني نحن السي بي يو لما كنا نعمله كان يكون typically this big elephant that can do any software program that I write. Now we're heading more into heterogeneous system, and by heterogeneous systems يعني في عندي module فيه GPU فيه CPU فيه associative processor or a vector processor وفيه FPGA, and each one of these modules is dedicated for a certain task. Or I have, for example, a specific neural network, for example, accelerators on chip, because we know that we are going to run lots of neural networks in the future. So now the software programming even is being dedicated for this parallel programming capability that we are exploiting to redesign the hardware. So there is a lot being done at the hardware software system level interface. So therefore, to break the memory wall, we're going to do distributed, or what we call near memory or in-memory compute. Okay, and this saves energy, and this saves performance and latency, basically reduces the latency. هيك لنطلع على الRAM device هيك at a high level. الRAM device هي عبارة عن metal with an insulator and a metal مثل ما حكينا. بحط عليها فولتج عالي، هالفولتج العالي بخليها تخلق فيلامنت وبتفش لي some ions يتخبوا بالالكترود. هيدي بتصير conductive filament. هيدا هو basically مثل ما حكينا. Okay, and then this filament can be programmed. Okay, يعني أنا بس أعمل له burning أو creation. أنا I can set it, apply a positive pulse. Okay, or I can reset it if I apply a negative pulse. بتفش الايونز اللي هن نيجاتيف ليعبوا الجاب ليعبوا الفيلامنت dots, and therefore they will create a gap in the conduction. بصير أنا بالهاي resistor state. Okay, so هل reset mechanism, or if I apply a positive voltage again, then I am going to really set it back. Sorry, هيدي. Then I am going to really set it. راحت هيدي منزوعة. Sorry. Okay, so I'm going to set it back. Okay, so the idea is now I can program my memristor to store whatever data I want, and then it is not going to lose its state until I program it again. هل ability to change the resistance by applying one big pulse or multiple pulses معناته أنا my resistor can learn. Okay, so it is similar to the synapse. إذا حطينا له spike أو حطينا له spike من هون يعني negative, then I can get increasing in the conductance or I can get decreasing in the conductance. So هالشي بيشبه the brain of the human. Okay. هلا حسب the programming strategy طبعا the device engineer work on improving the programming, okay, of the and the material. If I want to program, for example, let us say a 10K low resistor state اللي عم ببين عنا إنه 50% are around 10K، بس في عنا شوي منهم أصغر وشوي منهم أكبر. نفس الشيء ال 1 meg في عنا قسم أكبر منه وقسم أصغر منه لأنه نحن عنا process variation. هلا they are hoping إنه مش بس نعمل storing للزيرو وال1، إنه نقدر نعمل storing لintermediate values. ليش؟ لأنه ساعتها if I have, let us say, 4 values for the memristor, let us say 10K, 100K, 500K, and 1 meg, then I have 4 states, then I can really store 2 bits in my memristor. وكل ما أنا أقدر أحط multi bits، كل ما أنا عم بعمل الميموري اللي لإلي more compact. يعني أنا عم بقدر أحط more storage in smaller area. وهالشي طبعا is very interesting for the designers, بس they need to guarantee that there is no overlap. هلا طبعا التكنولوجيا عم تتطور، بس هون بنشوف بين level 1 و level 2 في عنا some overlap maybe with some low probability. So هون بصير study إنه أنا إذا عندي overlap بس with low probability, while my system at the high level, how much error it can tolerate. يعني إذا already neural network هي فيها error 70% وإذا أو 75%، إذا نزلت لل 73-72% منا أزمة. بس إذا نزلت لل 60 أو لل 50 طبعا it's a problem. And here where the design iteration بين application, okay, system level architecture and the low level implementation بصير في عنا trade-offs. And what are the implication and the application level of these different designs and trade-offs in my system. Okay, so هون عند بدنا window بين ال two states، وبهمنا أن يكون one state ما يكون عندها big spread. Okay, وفي عنا other properties اللي هن endurance و retention. يعني أنا قديش هيدي السيل إذا عملت لها programming قديه حتضاين تحافظ لي على هالvalue. If I keep reading from it, will it crash at their lifetime يلي هي لا إلا. Okay. هلا I'm going to skip here and I'm going to take you to this example. In the 1960s في واحد استاذ كبير اجى قال لهم look, I can create for you a multiply and accumulate using resistors. Okay, and he said, well, let us look at this. Let us assume that I have this wire here, okay, and in this wire here, let us assume that I have, for example, a resistor connected between this node and هيدا نرسمهم هون vertical بلون تاني بس حتى يكونوا واضحين هول horizontal pardon me. So هيدول horizontal lines, and between these horizontal lines and the vertical line I have a resistor connected here. لنقول الفاليو له هو R1. في عندي بين هيدا وهيدا another resistor اللي هو R2. بين هيدا وهيدا another resistor اللي هو R3. Okay, and let me assume that here I have مثلا at the end, at the bottom of this line, some current sensor, or I have here مثلا another resistor R, and I am measuring the voltage that is building up here. Okay, now let me assume that I am applying at this node here a voltage V1, and at this node here I'm applying 0. خلينا نشيل هيدا بس نعتبر هلا عم نقيس الكرنت حتى ما نصعب عليكم. خلينا نعتبر that we are sensing here the current that is passing through this line. Okay, that we are measuring I that is flowing here through some device. Okay, and let me assume that I'm applying V1 here, a 0 here, and then V2 here. What is the current that will flow in this device? شو هو الكرنت اللي حيقطع لي هون بهيدي الديفايس؟ هيك لنشوف. If I look at this resistor, اعتبروا انه هيدي هي شورت بس بتقيس الكرنت اللي مارق ما فيها شيء. يعني هيدي النود عم تمرق. شو عندي هون الفولتج هون؟ شو هو الفولتج هون ب R1؟ الكرنت عفوا. V1 على R1, right? And then what is the current in the second one? ما حيمرق لي current. صح؟ And in the third one, V3 على R3. So the current I that I am going to think or sense somehow, somewhere else, is really equal to the summation of VI على RI. صح؟ So فين اعتبر انه كأنه summation of VI ضرب 1 على RI، يعني هي summation of VI ضرب WI where W هي 1 على R. طيب in a neural network at a given node I really have an input X that will be multiplied by the weight W, an input X2 that will be multiplied by W2, and an input X3 that will be multiplied by W3. And the output of the neuron will be WI summation ضرب XI. Okay? فإذا they demonstrated to us that if we build with these memristors crossbar arrays, we are able to do multiply and add functions. And if we program those memristors to store some specific weight values, then we are able to realize the multiply and add locally without having to write from the memory to the CPU the value of the weight and the value of the x's, and then bringing back the summation of WI XI and storing it in the memory. Okay, so basically the current will be sensed and it will be reprogrammed into another block, and we will be able to build, they are hoping to build an architecture similar to the layers of the neural network to realize this whole neural network connections that we have, okay, in our design or in our architecture of the neural network. Okay, يعني بصير مثل ما عندنا functions or architectures that are available, we will have corresponding hardware architectures that can basically perform the function in parallel, okay, and locally. Okay, طبعا there are lots of optimizations happening, there are lots of issues that are being discovered, but this is basically where the research is heading. Okay, هلا هيدي implementation or هيدي بنسميها cross bar array. هلا إذا جينا اطلعنا really what are the other applications or the other topics that we are talking about in the project report. نحن حكينا أن الممرستر له multiple utilization. في عندي memristor based adders. اوكي سو الارم عم يستعمل بقلب اللوجيك. كيف عم يستعمل بقلب اللوجيك؟ مثلا I can build XOR gate using memristors. I can build an AND gate using RRAM. Okay, بس this type of logic بسموه MRL أو magic and other types of logic. هن فعليا بياخدوا two memristors وحسب البولاريتي للممرستر مذكرين انه هو عنده مثلا top electrode and bottom electrode. Okay, so if the top electrode, if this is the memristor and its top electrode, when we program it, when we apply a positive voltage here, we get it to be set. Let us look at this example, and when I apply, when the current flows in the opposite way, it becomes reset. هيك لنشوف بهيدا السيركت مثلا أنا إذا حطيت 1 و 0 كيف الكرنت بده يمشي؟ بده يمشي من الهاي لللو، صح؟ So إذا هو حيمشي من الهاي لللو حيمشي هيك. Therefore, what is going to happen, هيدا will be set, it will become R low، وهيدا ماشي الكرنت فيه بالعكس، صح؟ ماشي فيه صوب هيدي النود. So this will be reset, so it will become R high. طيب أنا هلأ في عندي لكينا 1، في عندي R low هيدي هي النود X، أوكي؟ في عندي R high وفي عندي 0. What is the value of X؟ هيدي النود 0 لأن، صح؟ The value of X will be a voltage divider اللي هو R high على R high plus R low ضرب 1، صح؟ So it will be high، بنعدها أنها حتكون high، وبيكون بهالfunctionality هيدي اللوجيك جيت لما أنا حطيت له 1 و 0 أوكي عطاني الأوتبوت اللي لإلي طلع 1. And using these techniques along with other transistors, they are able to realize the functionality of an adder, which mainly relies on XOR, or other architectures to implement different logic gates and different adder designs. هلا بنفس الوقت we are also using the memristor for in-memory computing. ممكن يستعملوه يا اما بالكروس بار اري اللي نحن حكينا عنه، اوكي، او ممكن يستعملوه بشيء بنسميه associative processor اللي هو مثل الفيكتور بروسيسور يلي بيعتمد على ternary cam، what they call ternary cam using memristors. اوكي، وهالشيء هو عبارة I am storing here connecting. Let us assume I just have the memristor and one transistor. اوكي، إذا هيدي هي R low أنا بعتت لها 1 هون هيدي will discharge، بس إذا هيدي هي R high أنا بعتت لها 1 هون then it is not going to discharge or will discharge weakly, and depending on the current here we see if we have a match or not. هلا هيدول البروسيسورز أو the in-memory computing عم يستعمل فيهم كمان الأسرام cells يعني if you recall the SRAM cell يلي قلنا هي عبارة عن 8 T cell يلي بتجيها pulse من هون وعندها read bit line هون, and as it is discharging things, okay, if it is storing a 1, but another peer cell, if it is storing a 0 here, then it is not going to discharge anything from this circuit. From this will not create a current. ليش فكروا فيه هن قالوا طيب عالما أنا إذا عندي, let us say I have a bit line and I'm just going to represent the cell by a 0 or a 1 and a 1, okay, so هيدا الويت هو it is stored in the SRAM cell, and then when I apply a pulse here, if I apply a pulse, this will be the input xi. If I don't apply a pulse بتكون xi 0. If I apply a pulse here بتكون xi هي 1. Okay. Then the amount of discharge from this capacitor will be really proportional to xi. يعني دلتا V على هالكاباسيتر حتكون proportional I يلي هي حتكون proportional ل summation of some factor ضرب XI ضرب stored value. بمعنى لو اجاني أنا على هيدا pulse ودارت الريد اللي لإله بس ما هو storing 0 يعني ما حيسحب لي charge، وهيدا ما اجى عليه pulse يعني ما حيسحب لي charge، وهيدا اجى عليه pulse و I'm storing a 1 يعني حيسحب لي charge. فهون وحدة من هيدول evaluated to 1 and the delta V will be proportional to 1 ضرب alpha plus 0 ضرب alpha plus 0 ضرب alpha بهالحالة. Okay, so if I can realize this multiply and accumulate, then I can realize any type of function. I can sense this voltage, apply it to a comparator, to an analog to digital converter, and find the data that I am storing or the multiply and accumulate result that I am going after. So هيدي هن عم يعملوا فيها الأسران neural network accelerators. طبعا في many other implementations أو in memory computing, and there are many recent applications to all of these designs. طيب. So لكن شفنا الRAM بآدر، شفنا الRAM بلوجيك جيت، شفنا الRAM بميموري، شفنا الأسرم بالmemory compute. طيب في عنا بعد mainly 3 topics. The third topic هي إنه في عنا devices اسمهم ferrofets، في عنا other non-volatile devices مثل الRAM عم يطلعوا جديد بيدعوا إنه هن عندهم new and better properties or different properties. So there is lots of comparison about the different types of non-volatile memory. هيدي هي more maybe on the device level بس في إلها applications. في عنا بعد another topic اللي هي RRAM based PUFs or physical unclonable functions. شو هو physical unclonable function? Physical unclonable function هو بيعتمد, if you recall I had a question in the beginning, إنه أنا إذا مطفي الأسرامز ومطفي السبلاي الVDD على هول memory وجيت دورتها للميموري, okay, if I turn it on it's going to initialize to random values. نحن فعليا الميموري فيها variability, okay, and not every time I try to read something I get the same response. يعني أنا إذا عندي chip 1 وعندي chip 2 ولو كان الديزاين هو ذاته, if I apply a specific excitation input, the same input I will get response 1 and I will get response 2 here because there is some variability on the chip. وهالشي هن عم يستفيدوا منه ليعملوا on chip key generation, هيدي للهاردوير security, okay, بشكل انه انا إذا أنا عندي my own key on my chip, nobody really can hack my system. But there are methods where I can somehow handshake with others based on my key, but nobody can steal my key and play as me. Okay, so هيدول هن physical unclonable functions, or there are many new ARM-based physical unclonable functions. وآخر شيء يلي هو عنا إياه كتوبيك هي ال approximate computing. Okay, and for approximate computing, it is mainly and really when we say, well, do I really want to have the perfect sum as the output of my ALU, for example, or can I have an approximate sum that saves me energy and that runs faster without affecting quality. فإذا نحن في عنا 3 factors mainly الفاستر يمكن الناس ما بقى عم يهتموا لها قد ما عم يهتموا على الانرجي because of the portable devices, and the quality because you cannot risk the quality for the customer. Okay, so this is the last topic. Let me just share a couple of slides about it from the computer. So let me share the screen. Let us look at this presentation. So if you look here, there are basically energy efficient computing specialization in the hardware. We are trying to have all of these heterogeneous systems, يعني Xilinx طلعوا I think many billion transistor system that performs many functions. And then there is also what we call the approximate computing. So the approximate computing that we talk about here, it is mainly takes into consideration the application in mind. Okay, it worries about at the system level what is happening, but basically we will implement here approximate hardware that will not hurt the quality, but they will be configurable, okay, such that we will not basically impact the application. وهون بيجي بيقلنا إنه نحن مثلا for example if we keep dropping VDD we will lose the accuracy of the system, but if we now do some trade-off or optimization on the system, okay, such that مثلا I sacrifice a little bit on the critical path, I play with my clock frequency, and then I apply some approximate computing techniques, then I can really save on the energy without compromising the quality. So the idea is we do not want to have too much complexity when we apply these approximations. And for example, let us say if we have an adder, for example, we can perform the most significant bits assuming some carry, or we can, without waiting for the carry to arrive from the least significant bits, for example. So all of these tricks and changes really depend on the quality and the energy trade-off. So we want our design to be quality energy aware system design. There are some optimal points which we aim for, and then we build the approximate computing. There's lots and lots of literature on approximate adders and other approximate computing, where in video processing or image processing or even in neural networks, the applications are not